So now somebody tell me what the derivative of m with respect to x is. What is the derivative of m with respect to x?
2x plus 2t.
Yeah. So maybe you can't see that that's a plus. Okay, so mx is 2x plus 2t. And what is the derivative of n with respect to t?
2t plus 2t? No, 2x plus 2t.
Yeah, 2x plus 2t. So they're equal, so this is exact. Okay, so I know it's an exact equation, so what is the next thing that I do to figure out what f is? What are the next steps that I take? So I know it's exact because mx is equal to nt. What is the next thing that I do to try to figure out what f is?
We can take the integral of either m or n with regards to the other or the opposite variable.
Yeah, exactly. So I know that m is the partial derivative of f with respect to t, for example. So then f of tx, I know is going to be the antiderivative of m, x squared plus 2tx plus 2t with respect to t. But then remember, I always have to add in this arbitrary function of x. Okay, because when you take the antiderivative, you have to add an arbitrary constant. We've got two variables and we're taking the derivative, or sorry, we're taking the antiderivative with respect to t. And so the arbitrary constant is going to be a function of f, or sorry, a function of x, because the derivative of h of x with respect to t is equal to 0. Okay, so the derivative of what I just wrote down with respect to t is equal to m. Okay, so the derivative, what is the derivative of x squared with respect to t? Yep, that's right. Tx squared. The derivative of 2tx with respect to t is t squared x, then plus t squared plus h of x. Okay, so I almost know what f is. I just need to figure out what h is. How can I do that? How can I figure out what h is?
Take the partial derivative of f with respect to x.
Yeah, so I know that n is equal to the partial derivative of f with respect to x. So I know the partial derivative of f with respect to x is equal to n. That's 2xt plus t squared plus 3x squared. Okay, but I also know this is f, that thing that I just circled as f. So if I take the derivative of that with respect to x, that's another way to find the derivative of f with respect to x. So that circled part is f. So if I take the derivative of that with respect to x, it is equal to this other form that I have for the partial derivative of f with respect to x. Okay, so when I take the derivative with respect to x, I get 2tx plus t squared plus h prime of x. Okay, notice what this leaves me with. So the t squared cancels, the 2xt, the 2tx cancels, and what I'm left with is h prime of x is equal to 3x squared. Okay, so this is good. So if you got something like h prime of x is equal to something like this, all of the t stuff should cancel. Okay, so if you have t stuff left, it either means the equation is not exact or you made a mistake somewhere. But none of the t stuff is left, so this gives us confidence that we've done everything correctly so far. So h prime of x is equal to 3x squared. So this means h of x is going to be x cubed plus some constant. And so f of tx is equal to tx squared plus t squared x plus t squared plus h of x, which is x cubed, plus some arbitrary constant. Okay, now if you come back up here to the equation, the left-hand side of the equation, this part right here is the derivative of f with respect to t, and that's equal to 0. So if the derivative of f with respect to t is equal to 0, it means that this is actually equal to some constant, and we're just going to absorb that c into that constant over there and just write it like this. Okay, and this is the general solution. If you had a final solution, if you had an initial condition, you can figure out what c is and do some other stuff.
1, 2, 3, almost 4.
My colleagues are measuring my office to make sure I don't have one that's bigger than theirs.
No, that's not what
That's
they're
not why
doing.
they're doing that. That's not why they're doing that.
But how many long is it? 1, 2, 3, 4.
Okay.
So it's 4 by 4.
Are there any questions on this problem? All right, so I'm gonna go down and get some
16
coffee and figure out some questions if you have them when I get back.
Yeah, but it's 4.5 that way. And it's almost 5, because it's really 5 if you have a window. Like, the amount the window would be, that's 5 across. And it's 1, 2, 3.5, yeah. 5. Sorry.
Okay. Were there any questions on that problem? I assume not.
I got one question, and it's
Yes.
related to the constant at the end. So we figure out that hx is x cubed plus c.
Uh-huh.
So we add that to our m of x, and we're allowed to move that c constant to the right of the equal sign, because that's how constants move, right?
Right.
Okay.
Yeah.
Okay, then I understand it up to that point.
Okay. All right. Okay, find the general solution to this differential equation. Okay, somebody give me a method that we can use for this.
Can't you split them and then take the integral both sides?
Yeah, exactly. So this is a good separable equation. I can put all of the t stuff on one side, or more descriptively, put all of the x stuff on one side and leave the t stuff where it is. And so I can write this as 1 over 1 plus x dx dt is equal to 3t squared over 1 plus t cubed. Okay, so when you can do it like this, when you can write it as some function of x times dx dt is equal to some function of t. It's called a separable equation. The idea is that the left-hand side, okay, so if I have, if I have some function f, that's a function of x, and x is a function of t, then the derivative of f with respect to t is going to be equal to the derivative of f with respect to t times the derivative, the derivative of f with respect to x times the derivative of x with respect to t. Okay, and so this right here is like what you get if you do chain rule. Okay, so in other words, f of x is just going to be the antiderivative of 1 over 1 plus x, which is equal to the natural log of 1 plus x plus c. But notice what we're saying, notice what we're saying is that the left-hand side is equal to the derivative with respect to t of f. So this is f of x. Okay, and when you take the derivative of this with respect to t, you just get, 1 over 1 plus x. So in other words, the left-hand side is equal to the derivative with respect to t of 1, of the natural log of the absolute value of 1 plus x. Okay, because if you compute the derivative of this expression of the natural log of 1 plus x with respect to t, you're going to get 1 over 1 plus x times the derivative of x with respect to t. And again, that's just by the chain rule. And so this is equal to 3t squared over 1 plus t cubed. Okay, and so now to get to x, what do we do? So we want to figure out what x is. We want to solve this for x. So what do we do now? I want to solve this equation for x. What do I do now?
Take the integral of both sides.
Yeah, so we're going to take the antiderivative of both sides. Yeah, or exactly what both of you all said. Yeah, so the antiderivative of the left-hand side with respect to t is the natural log of 1 plus x. And this, well, what is the antiderivative of, so in other words, I'm going to do this. So what is the antiderivative of 3t squared over 1 plus t cubed? What is the integration technique we use for that?
U sub.
Yeah, u sub, we're going to say u is equal to 1 plus t cubed. If that's the case, then du dt is equal to 3t squared. So this is just going to be the antiderivative of 1 over u. So that's going to be the natural log of u, or the natural log of the absolute value of 1 plus t cubed plus a constant. Okay, so now I want x, so I'm going to raise both sides to the power of e, and I've got the absolute value of 1 plus x is equal to e to the power of c, which is just another arbitrary constant we'll call a, times the absolute value of 1 plus t cubed. Okay, and note that the absolute value, all you're doing is multiplying by plus or minus 1. Okay, if 1 plus x is negative, the absolute value of 1 plus x is just negative 1 plus x. Okay, if 1 plus t cubed is negative, the absolute value of 1 plus t cubed is just minus that. So those are just constants, and we can absorb those constants into the a and write this as x plus 1 is equal to a times 1 plus t cubed. And now we can solve. We get x of t is equal to a times 1 plus t cubed minus 1. Okay. Any questions on this one?
I got kind of lost on where you got a from.
Oh, okay. So let me do one more step. So here, going from the step above to where I am now, I'm going to raise both sides to the power of e, and it's e to the power of c times e to the natural log of 1 plus t cubed. E to the power of, I'm sorry?
Would it not be plus there instead of times?
Well, so if I have e to the natural log of 1 plus t cubed plus c. By identities about exponentials, this is e to the c times e to the natural log of the absolute value of 1 plus t cubed.
Okay, that makes much more sense. Thank you.
Yeah, and e to the c is just an arbitrary constant that I'm going to call a. And e to the natural log of something is just equal to something. So now this is the absolute value of 1 plus t cubed, and then you can go down to that step. Any other questions? So now another way to do this problem that I don't like, but I'll sort of talk about it, is to write this as 1 over x plus 1 dx dt equals 3t squared over 1 plus t cubed. And now we're going to literally move all of the x stuff to one side and t stuff to the other side, meaning we're going to sort of multiply both sides by dt. And so we get dx over x plus 1. Whoops. Dx over x plus 1 is equal to 3t squared over 1 plus t cubed dt. And now we're going to take the antiderivative of both sides. And now we get essentially back to where we were before. The left-hand side is a natural log of the absolute value of x plus 1. And the right-hand side is a natural log of the absolute value of 1 plus t cubed plus c. Okay, really there's an arbitrary constant here as well, but we're just going to put them both on one side. And since we're solving for x, it makes sense to put it on the t side. Okay, so I don't, I put that there because I know that's how other professors teach it, and I'm fine with students in my class doing it that way. But I don't like doing it because I don't like talking about multiplying both sides by dt, for example, since we don't really know what that means. It's just kind of a magical thing that I'm allowed to do, and you're allowed to do whenever I tell you you can, but you don't know when else you're allowed to do it. So anyways, that's sort of a valid method, most people would say. All right, are there any questions on this problem?
Probably 525.
Okay,
I only got one question because I was looking at it in the previous method, the first one you showed us.
Yeah.
From the step that you go fx equals the derivative of 1 over 1 plus x. Later on, you get dt times natural log of 1 plus x. Where does the d over dt come from? Like,
well,
yeah.
are you talking about right here?
Yeah, so where does that d over dt come from that is being multiplied by the natural log of 1 plus x?
Right, so the derivative of the natural log of 1 plus x with respect to t is equal. That's what all of this discussion was up here. So if I have f as a function of x and x is a function of t, then the derivative of f with respect to t is equal to the derivative of f with respect to x times dx dt. Okay, so f of x is equal to the antiderivative. So f of x is equal to the antiderivative of 1 over 1 plus x, which is equal to the natural log of 1 plus x. So f of x, I'm just using this, f of x is equal to the natural log of 1 plus x. So that just comes from that formula.
I see. Okay, I'll remember that.
Okay. All right. So let's go here. All right, x prime plus tx is equal to t. Okay, this is a first order linear equation. When we have a first order linear equation, there's kind of two things we can do. If it's homogeneous, we can, we can write it as a separable equation. If it's not homogeneous, we can use integrating factors. Okay, so this is a first order linear non-homogeneous equation. So we're going to use integrating factors. Okay, that's one way to solve it. There's other ways to solve it, but we're going to use integrating factors. Okay, so what is the integrating factor for this problem? No, so the integrating factor is not x. So remember, okay, so if we have an equation of the form, so let's do a little sort of review here. Okay, so if we have an equation of the form x prime plus p of t x is equal to q of t, then what is the integrating factor equal to?
Is it e to the 1/2 t squared?
Well, yeah, so where does that formula come from?
Oh.
Like just in terms of p, So look at just this part right here, this brown box here. What is the integrating factor for an equation like this?
E to the integral of p of t dt.
Yeah, exactly. So it's going to be e raised to the power of the antiderivative of p. Okay, and as several of y'all have said, in this case, mu of t is going to be e to the power of the antiderivative of t. And so the antiderivative of t is 1/2 t squared. So it's going to be like this. Okay, so now that we have the antiderivative, or sorry, not the antiderivative, wow. Now that we have the integrating factor, what's the next thing that we do?
Multiply it by both sides of the equation.
Yep. Hold on 1 second. Yeah, so we're going to multiply both sides of the equation by mu. And when you multiply both sides of the equation by mu, remember the whole reason, like I'm not going to tell you where mu comes from, but the whole reason we pick this mu is because when you multiply the left-hand side of the equation by mu, it becomes x of t. It becomes the derivative of x of t times mu of t. So when you multiply the left-hand side of the equation by mu, you get x times mu prime. And then when you multiply the right-hand side, you get just whatever it is. No identity there. Okay, and the reason we like this is because now this becomes a separable equation, but instead of being kind of separable in the x variable, it's separable in the x times mu variable. Meaning, another way I can write this left-hand side is the derivative with respect to t. Now I can take the antiderivative of both sides, and I've got x of t, mu of t on the left-hand side, and on the right-hand side, I have t e to this t squared over 2 dt. Okay, and now for this antiderivative, how do we do it? How do we find the antiderivative of t e to the t squared over 2? Everybody understands? Say it again.
U substitution.
Yeah, u sub. And what are we going to say u is equal to?
T squared over 2.
Awesome. And then what is du dt going to be?
T.
T. Okay, so now I come over here. Okay, I replace stuff. Well, du dt, that's t. So I'm just going to have e to the u. Du to the antiderivative of that is e to the u. So it's e to the t squared over 2 plus c. Okay, so then x of t And of course, I'll go ahead and write mu here. Mu is e to the t squared over 2. So then x of t, if I solve for x, if I multiply or if I divide both sides by e to the t squared divided by e to the t squared is just 1 plus c e to the minus t squared over 2. Like that. And so that is the general solution. And again, if you had an initial condition, you could figure out what C is. Okay, are there any questions on this problem? Let me pause here for just a moment again.
I'm trying to understand, why did the exponential for e turn negative?
Because I divided, are you talking about right here?
Yeah.
Well, I have this expression, x of t, e to the t squared over 2. And now I want to solve for x, so I'm dividing both sides by e to the t squared over 2.
So when you don't, doesn't it happen that when you divide exponentials, they subtract? So wouldn't that be a 0? Or am I misunderstanding?
Well, so I've got both of these terms over here.
Ah, yeah, I see.
Okay, anything else? Okay. All right, so now, okay, so I don't know what your professor is going to let you use on the exam, but if you're in my class, I don't know what if you're not in my class, I don't know what your professor is going to do, but if you're in my class, you can use, you're going to be able to use, you'll have access to a Laplace transform table that I'm going to give you. Okay, but for this, I want to find the inverse, I want to find the Laplace transform of the solution. So in other words, I need to also tell you, x of 0 is equal to 0, x prime of 0 is equal to 1. So I want to find the Laplace transform to the solution of this initial value problem. So I just want the x of s. I don't want to invert that to find x of t. I just want x of s. Okay, so I want to start by taking the Laplace transform of the left-hand side. Okay, so I'm going to need to know what the Laplace transform of x prime is. So somebody tell me what the Laplace transform of x prime is.
X of s minus x of 0.
Yeah, exactly. Xs of s minus x of 0. Perfect. And what about the Laplace transform of x double prime of s?
S squared f of x of s minus x of s x of 0 minus x prime of 0.
Yeah, perfect. Yeah, there's a lot of letters. Okay, so now the left-hand side, so let's just plug this in. So the Laplace transform of x double prime is s squared x of s minus s times x of 0, but x of 0 is 0, minus x prime of 0, and x prime of 0 is 1, plus 3 times the Laplace transform of x prime, that's s times x of s minus x of 0, but x of 0 is 0, so it's going to be like this, minus x of s. Okay? Now, what is the Laplace transform of delta of t minus 4? What is the Laplace transform, excuse me, of delta of t minus 4? In other words, that part right there. What's the Laplace transform of that?
Isn't it something to the -4? E to the -4?
All right, you sort of, I didn't hear what you said. Say it one more time.
I could be wrong, but isn't it e to the -4?
No, it is
Yeah.
correct. It should be e to the -4s, right?
Yes, I heard to the -4s, but didn't get what you were raising. Yeah, that's exactly right. So it's e to the -4s. And what is the Laplace transform of u1 of t?
Wouldn't it be e to the -s? No.
Close. That's definitely part of it.
E to the over s?
Yep, like that. Okay, so now I want to solve for x of s. So it's kind of a shortcut. On the left-hand side, you're always going to have x of s times the characteristic polynomial. So s squared plus 3s minus 1, and then we have the leftover parts, meaning the parts that are multiplied by x of s. So in this case, it's just minus 1. And this is equal to e to the -4s plus e to the -s over s. Now I'm going to add 1 to both sides. And I've got x of s times s squared plus 3s minus 1 is equal to e to the -4s plus e to the -s over s plus 1. And now I divide to get x of s. So x of s is equal to e to the -4s over s squared plus 3s minus 1 plus e to the -s over s times s squared plus 3s minus 1, and then minus 1 over s times s squared plus 3s minus 1. And that's it. That is the Laplace transform of this solution. Or sorry, yeah, that is a Laplace transform of the solution to this differential equation. Okay.
Would it be a +1 on that last like that last term?
Oh, shoot. Yeah, right. Whoops. Yeah. So there's a plus there. There needs to be a plus there. Is that what you're talking about, Isaac?
Yeah.
Thank you. So let me put it in red so you can see where I made the mistake.
There's no next step after that, right? This is the solution.
Yeah, this is the Laplace transform of the solution to the differential equation. If you wanted to know the solution to the differential equation, we would now have to find the inverse Laplace transform, but that's not what we asked.
I
That's
see.
what I asked, yeah. Why is there an additional s? Oh, shoot. I'm sorry. Thank you, Austin. I don't know what happened. I was just getting carried away. So I had an s there. There didn't need to be an s there. Thank you, Austin. That's not a 0 either. That's where I made a mistake. Yeah. I was just copying down quickly. Okay. Thank you. Sorry about that. Anything else? Okay. All right, find the inverse Laplace transform of this. Okay, so what is the first thing that we want to do? So when we have something like this, what's kind of the first thing that we want to do when we find the inverse when we're finding the inverse Laplace transform for something like this?
We take the e's out of the numerator and put them in front.
Yeah, exactly. So we're just going to separate the e stuff and the non-e stuff. So this is e to the minus s minus e to the minus 2s times 1 over s squared minus 2s plus 5 times s minus 1. And the reason that we want to do that is because there's an identity that says that the Laplace transform of uc of t times f of t minus c is equal to e to the minus cs times f of s. Or sorry, not equal, so meaning like this. The Laplace transform of the thing on the left side of the arrow is equal to e to the minus cs f of s. And so basically the hard work is going to be figuring out the inverse Laplace transform of that. Okay, does this make sense to y'all? Okay, so now I'm going to find the inverse Laplace transform of this part right here. And so this is 1 over s squared minus 2s plus 5 times s minus 1. So I want to find the inverse Laplace transform of that. Okay, now for something like this, what is the first thing that I'm going to need to do?
Don't you want to create, what's it called? Like a perfect square for you to divide?
Well,
Like
so
to separate them, I mean.
So before we do that, we need to do something else. So who was about to say something?
I was going to say partial fractions.
Yeah, so we're going to do partial fractions. First, I'll just note that s squared minus 2s plus 5, that's irreducible. So you can't factor it using real numbers at least. Okay, and here we go, s minus 1. And what goes over the s squared minus 2s plus 5?
Ax plus b.
Yeah. But remember to use s since those are the variables. And then what goes over the s minus 1?
C.
C, exactly. Okay, and so now what we're going to do is we're going to solve for A, B, and C. So you might have different like shortcut ways of doing this. I'm going to tell you how I'm going to do it. It works for any sort of partial fraction setup, but again, however you want to do it is fine as long as it's mathematically valid. I'm just going to do the one that works for everything. So step 1, I'm going to clear denominators, and so I get 1 is equal to as plus b times s minus 1 plus c times s squared minus 2s plus 5. Okay, so now I'm going to equate coefficients. So I'm going to see what is the power. So I've got a second degree polynomial on the right hand side. And so whenever I have two polynomials that are equal to each other, the corresponding coefficients are equal to each other. Okay, so what is the coefficient of s squared on the left hand side?
0.
0. Okay, let's try to figure out the coefficient of s squared on the right hand side. Well, from the first term, I could have as times s, so that gives me an s squared. And from the second term, I could have c. Okay, so what is the coefficient of s on the left-hand side?
0.
0. And let's try to find the coefficient of s on the right-hand side. So I could, for this first term, how do I get an s? I could do as times minus 1. That's minus a, or I could do b times s. That's plus b. And then for the second term, I'm only going to get a an s if I do c times minus 2s. So this is going to be minus 2c. Okay, and then finally, whoa, that was supposed to be an s. What is the coefficient of s to the power of 0 on the left-hand side?
1.
1, that's right. And okay, what do we get on the right-hand side? Well, if I do b times minus 1, that'll get me a constant, and then plus 5c. Okay. Everybody okay with that? Okay, so let's think about this. So this bottom equation tells me that b is equal to 5c minus 1. This top equation tells me that a is equal to minus c. I'm going to take both of those expressions and plug them into the middle equation. In the middle equation, I've got minus a, so minus a is equal to c, so 0, okay? So I'm plugging it into the middle equation now. Minus a is just equal to c plus b, so that's going to be plus 5c minus 1, and then minus 2c. Okay, what does this turn out to be? We've got c plus 5c, that's 6c. 6c minus 2c is 4c. So this is 4c minus 1. So this tells us that c is equal to 1 over 4. Okay, if c is equal to 1 over 4, then a is equal to minus 1 over 4. And then this is going to be 5/4 minus 1. So 5/4 minus 1 is just going to be 1/4. Okay, so let me write down what we have. X of s is equal to something. So a is minus 1/4, so this is going to be minus 1 over 4s plus b. B is 1/4, so plus 1/4. And then we're going to divide by s squared minus 2s, s squared minus 2s plus 5, and then plus something over s minus 1. Okay, c is equal to 1/4 as well. So this is what x of s is. That everything we've done so far is just to get to this point. Now we still need to find the inverse Laplace transform, but I want to make sure everybody understands where we are so far. It's just partial fractions, which I get, is tedious.
Is the a plus c, is that an s equal s?
Where's that?
A plus c for the s squared, where you're plugging in the coefficient of 0, you have a plus c equal, and I think that's supposed to be an s, or I don't know.
So I've got 0 is equal to a plus c. This implies that a is equal to minus c.
I see.
Okay. All right. So now basically, to do the next part, let me zoom in a little bit. I want to start by factoring out the 1/4. So I'm going to have minus 1/4 times s minus 1. Okay, I'm going to complete the square in the denominator. That's going to give me s minus 1 squared minus 1 plus 5. So plus 4, and then plus, so that's this part, and then plus 1/4, 1 over s minus 1. Okay, so now I've got minus 1/4 So if I want to find the inverse Laplace transform of this piece, well, will somebody tell me what it's kind of like? What does this remind you of? Which entry in the Laplace transform table does this most remind you of?
Cosine or sine? Like,
Yeah, close. So not cosine or sine, but something close to that.
E to the AT cosine of BT.
Yeah, so whenever you've got this kind of like, s minus something over s minus something squared plus something, this is like an exponential times a trigonometric function, okay? And you need to make sure the A is going to be whatever those entries are, or whatever those guys are. So if they're different from each other, then you've got to kind of mess around a little bit. But if they're equal to each other, if they're equal to each other, you don't. Okay, so let me just make sure I wrote everything down correctly here. C is a quarter, A is minus, and then 5. Okay. All right, so, whoops. This is A. So in this case, A is equal to 1, and B squared is equal to 4. So the inverse Laplace transform of this part in the brackets is e to the t cosine 2t. And what is the inverse Laplace transform of this part? What is the inverse Laplace transform of 1 over s minus 1?
E to the T.
Yeah, e to the t. Okay, so then the Laplace transform, or the inverse Laplace transform, just of this part, the inverse Laplace transform is minus 1/4 e to the t cosine 2t plus 1/4 e to the t. Now we're going to remember we have this exponential stuff here, and this, going to use this identity. And so the Laplace transform, or the inverse Laplace transform, is x of t is equal to u1 of t times minus 1 over 4 e to the t minus 1 cosine 2 t minus 1 plus 1/4 e to the t minus 1 minus u2 of t times minus 1/4 e to the t minus 2 cosine 2 t minus 2 plus 1 over 4 e to the t minus 2. That is the Laplace transform of everything. So that's the final answer, what I just wrote there. Okay. Are there any questions on this one? Let me pause here for a moment again and see if there are any.
I just had an issue with when you were doing the partial fractions, or when you were figuring out the coefficients. I was kind of lost on the coefficient part.
This right here, where I'm finding A, B, and C.
Yeah, I kind of got confused there. I don't think I've done that method. I've done it another way.
Well, however you want to do partial fractions is fine with me. This is how I did it. Those 3 equations you have there, or that I have there, that's just a system of 3 equations and 3 unknowns. I've got 0 equals equal to A plus C, 0 is equal to minus A plus B minus 2C, and 1 is equal to minus B plus 5C. Okay?
But are you like plugging it into the previous 1 equal AS plus B times S? Like, I don't know how you're plugging it in, because I just want to understand all methods,
Yes. Well, okay. What I'm doing is I'm equating coefficients. So I've got a quadratic, I've got 2 polynomials, I've got an equal sign here, okay? I've got a polynomial. Anytime I have 2 polynomials that are equal to each other, I know the corresponding coefficients are equal to each other. Okay, so I know the coefficient of s squared on the left-hand side is 0, because the left-hand side is 1. So the coefficient on s squared on the left-hand side is 0. And on the right-hand side, I figured out, the A plus C, that's just the coefficient of s squared on the right-hand side.
Okay, I see.
Yeah. All right. Okay, so I'm going to pause here for a moment, walk down and refill my coffee, and I'll be back. Feel free to either wait till I come back to ask a question or put it in chat if you want to, and I can look at it when I get back. So the question, why do you have a 2? Because the Laplace transform of that part is just cosine of 2t. Does that answer your question, Bryce? So the question is, why do I have a 2 between cosine and t minus 2? And that's because it's okay. All right. Okay. So now we're going to find the general solution to this differential equation. Okay, there's kind of a general procedure when we're finding the general solution to a second order, a non-homogeneous second order equation like this. Somebody walk me through it.
We need the solution to the corresponding homogeneous equation first.
Yeah, exactly. So we're going to find the solution to the corresponding homogeneous equation, and then do something to find a particular solution to the non-homogeneous equation. Okay, so first of all, we're going to try to find the solution to x double prime minus 2x prime plus x is equal to 0. Okay, how do we do this? How do we find the general solution to this equation?
Characteristic polynomial.
Yeah, exactly. So the characteristic polynomial is r squared minus 2r plus 1. And this is r minus 1 squared. And so when you have something like this with a repeated root of the characteristic polynomial, the solution, so the h here means solution to the corresponding homogeneous equation, what is the general solution equal to?
C1 e to the t plus t C2 e to the t.
Yep. So C1 e to the t plus C2 t e to the t. Okay, so that is the solution to the corresponding homogeneous equation. Now I'm going to use the method of undetermined coefficients to find the particular solution. Okay, so if the right-hand side is t e to the t, your initial guess should be at plus b e to the t. That should be your initial guess for the particular solution. Okay, this is just based on the chart that's in the book or just thinking through it. Okay, but what is the problem here?
This is a solution.
Yeah, so at plus b e to the t is a solution to the corresponding homogeneous equation. So what do we do in a case like this?
Multiply by t.
Yeah, so we're going to multiply it by t. What about that? Are we okay now?
No,
And why not?
because we still have a solution.
Yeah, exactly. So we have to keep multiplying the particular solution by t until none of the terms are a solution to the corresponding homogeneous equation. So if you distribute that t, you're going to get at squared e to the t. That's not a solution to the corresponding homogeneous equation, but you're also going to get plus bt e to the t, and that is a solution to the corresponding homogeneous equation. Okay, because if one of the terms is a solution to the corresponding homogeneous equation, when you plug xp into the left-hand side, that's just going to be equal to 0. So it's like it's not even there. Okay, and so now we need to multiply it by t again. And so our guess is going to be at cubed plus bt squared times e to the t. Okay, is everybody okay with that? Okay. All right, so now what we're going to do is we're going to take the derivative of x, or of xp, we're going to take the second derivative and plug it into the equation and do this equating coefficient thing again. Okay, so xp prime of t is equal, so I'm going to do the product rule. This is 3a t squared plus 2b t e to the t plus at cubed plus bt squared e to the t. And now I need to take the second derivative, xp double prime of t. Okay, what's this going to be equal to? Well, I'm basically going to do the product rule twice. So I'm going to get, when I do this, so I'm going to get 6at plus 2b e to the t plus 3at squared plus 2bt e to the t. So that's just the derivative of this first term. Now I'm going to add the derivative of the second term. Okay, but notice when I do the derivative, so the second term, the derivative of the thing in the parentheses is just equal to that. And so when I do the product rule here, I'm just going to get another one of these terms. So I'm just going to add a 2 there, and then plus at cubed plus bt squared e to the t. Okay, and now kind of, conceptually, I'm going to plug this in to the left-hand side of the equation, set it equal to the right-hand side, and do this equating coefficients things. And the coefficients, the kind of how I'm going to organize it, I'm going to look at the coefficient on t cubed e to the t, t squared e to the t, t e to the t, and just e to the t. So I'm going to equate coefficients on both sides. Okay, one thing to keep in mind here is that that's going to give me 4 equations. I only have 2 unknowns, so I only really need 2 equations. Okay, so it's best to kind of have as few equations as I possibly can. So the observation that I want you to make is that if you look at the coefficient on e to the t, see, we're going to have to plug xp prime, and xp double prime into this, and that's going to get messy. We're not actually going to plug it in. We're just going to try to look through to see what's going to happen if we did plug it in, okay? But notice that if you look at xp prime, and xp double prime, the only one of those that has an e to the t term is xp double prime. That's the only one with an e to the t term, and it only appears right here. Okay, and similarly, if you look at t e to the t, okay, so notice that xp has no t e to the t term. It's just xp prime and xp double prime that have a t e to the t term. Okay, so we're just going to use these two equations. Okay, so if I start with e to the t, what is the coefficient on e to the t on the right-hand side here? What is the coefficient on e to the t?
Zero.
Yeah, 0. Okay, now I'm going to try to find the coefficient of e to the t on the left-hand side. Well, again, e to the t only appears in the xp double prime. So xp double prime is just 1 times xp double prime. So the coefficient on e to the t on the right-hand side is 2b. Okay, and this right away tells me that b is equal to 0. Okay, so now I'm going to look at the t e to the t equation. What is the coefficient on t e to the t on the right-hand side?
One.
Yeah, 1. Okay, so now it's a little trickier to find a coefficient on t e to the t on the left-hand side, but let's work through this. So I've got xp double prime. I've got 6at. So 6at times e to the t. That's going to give an e to the t coefficient. And from this term right here, I'm not going to have any more t e to the t terms. Okay, over here, notice I have a 2 times 2b t e to the t. That's going to give me a t e to the t term, but p is equal to 0, so I don't need to care about that. And then when I come up to xp prime, there's going to be e to the t terms there. But notice the only e to the t term there is the 2b, and that's equal to 0. Okay? So I just have this equation, 1 is equal to 6a. This implies a is equal to 1/6. And so this tells me that xp of t is equal to 1/6 t cubed e to the t. And then so overall, x of t is going to be equal to the solution, the general solution to the corresponding homogeneous equation plus the particular solution. So this is c1 e to the t plus c2 t e to the t plus the particular solution 1/6 t cubed e to the t. Okay, are there any questions on this one?
So not as much of a question, it's just to, like, I guess, confirm, but at the when you're initially defining xp of t, from at plus b to at cubed plus bt squared, when you're determining that, that's just because you don't want to have whenever you do put it in as a particular solution, you don't want to have like a t that's the same term as something that's already in the general solution.
Yeah, exactly. Yeah, so let me come over here and
I was just making sure that was the reason why.
Yeah, so we started with like at plus b e to the t, and if we were to sort of distribute the e to the t, this would be like this. And both of these are solutions to the corresponding homogeneous equation. Yeah, and we know that, you know, there's two ways we could figure that out. One is because we already found the solution to the corresponding homogeneous equation, or we could literally just plug them into the equation and see that they're equal to 0. And see, when we plug a t e to the t and b e to the t into the equation, it's equal to 0. So what we do next is multiply by t. So we get something like this. And the a t squared e to the t, that's fine. But the b e to the t, that's also a solution to the corresponding homogeneous equation. And so we multiply by t again to get this. But I think you understood that, but I wanted to just say it again for everybody. Okay. So whenever you use the method of undetermined coefficients, you kind of start with an initial guess and then keep multiplying that guess by t until none of the terms are solutions to the corresponding homogeneous equation. All right, any questions? Okay. Okay, so let me go back up to the top here. Okay, so let's find the general solution to this system of equations. Okay, so somebody's just kind of very like overhead view. Somebody walk me through how we're going to do this. How do we find the solution to a 2x2 system like this?
Yeah, first find the eigenvalues for the matrix.
Exactly. So first step is find the eigenvalues and eigenvectors, and then depending on different properties of those eigenvalues is kind of going to direct what we do. So we're going to look at so eigenvalues first. The determinant of -1 minus lambda, -4, 1, -1 minus lambda. We set this equal to 0. So this is going to be lambda plus 1 squared plus 4. And we're going to set this equal to 0. And we see we're going to have complex eigenvalues, right? And so we're going to have the eigenvalues, lambda 1 and 2, are equal to -1 plus or minus 2i.
Is it a negative one or a positive one?
A positive one, because I'm going to subtract 4 and then I'll have lambda plus 1 squared.
Oh, I meant like in the lambda itself. Like, did we pull a negative out to make it lambda plus 1, and so
Yeah.
we would still have a
Right.
negative
So
to multiply?
say that again.
I mean, yeah, like how technically how it's like -1 minus lambda, we're squaring that so we can like
Yeah.
pull out a negative.
Yeah.
All right.
Right, and those two negatives, so it's -1 minus lambda squared, which is minus lambda plus 1 squared. So the minus, minus times minus is plus. Okay, and so now we need to find the eigenvectors. Okay, so I'll just take lambda. I'm going to call lambda is equal to -1 plus 2i, and so I'm going to look at the system. -1 minus -1 plus 2i, -4, 1, -1 minus -1 plus 2i times xy is equal to 0, 0. Okay, so what does this system become? So let's just rewrite this. So because there's a lot of minus signs and the complex and the imaginary numbers. So -1 minus -1. Okay, -1 minus -1 is 0, right? So I'm just going to have minus 2i, -4, 1, and then this will be minus 2i again. Xy equals 0, 0. Okay, so this says minus 2ix minus 4y is equal to 0. That's what the top equation says. The bottom equation says x minus 2iy is equal to 0. Now remember, at this point, we always want to check to make sure, you always want to check to make sure that these equations are multiples of each other. So notice that the bottom equation, so notice that if I multiply the bottom equation by minus 2i, I get the top equation. If I multiply the bottom equation by minus 2i, I get the top equation. This is because 2i times 2i is minus 4i, and then, yeah. So again, if I multiply the bottom equation by minus 2i, you get the top equation. So this tells us that what we're doing is right. Does that make sense to everybody? It gets a little tricky, obviously, when you're dealing with complex numbers. Right, so if you first just think about multiplying that bottom equation by 2, you're going to get 2x minus 4iy. Then if you think about multiplying it by a minus sign, you'll get minus x plus 4iy. And then when you multiply that by 2, you'll get, or by I, you'll get 2ix minus 4y. Okay, just think through that. I know that might have been hard to follow, but just note that if you multiply the bottom equation by minus 2i, you get the top equation. And basically, that check is good because if we've done something wrong, there's almost no way. So if the two equations are not multiples of each other, it means we've done something wrong. On the other hand, if we've done something wrong, there's almost no chance that just by accident, the two equations are going to be multiples of each other. Okay, either way, the easiest equation to solve is the bottom equation. It says x is equal to 2iy, or maybe it's better to write this as 2yi. Okay, and so any vector, except for the zero vector, any vector where the top entry is 2i times the bottom entry is going to be an eigenvector. So for example, we could have 2i and 1. This is an eigenvector. Okay, and remember when we've got complex eigenvectors and eigenvalues, the general solution is equal to C1 times the real part e to the lambda t times v plus C2 times the imaginary part of e to the lambda t times v. Okay, so now we need to find the real and imaginary parts of e to the lambda t v. Okay, so e to the lambda t, this is e to the minus 1 plus 2it. I think that's what I pick. I think that's what lambda is, right? Yeah, minus 1 plus 2i times the vector, which is 2i1. Okay, and so we'll start like this. And so what we're going to do is we're basically going to write the exponential in terms of its real and imaginary parts, and we're going to write the vector in terms of its real and imaginary parts, multiply those, and split those into their real and imaginary parts. Okay, so for the exponential, this is going to be, actually, I'm going to do a little pre-processing. This is e to the minus t, e to the 2it times 2i1. I'm basically just going to leave that e to the minus t alone and just keep copying it down. Okay, so inside here, e to the 2it, by Euler's identity, this is cosine of 2t plus I sine 2t, and we're multiplying it by the vector 2i1. So this is 0, 1 plus I 2, 0. Okay, let me make these outer parentheses like big parentheses or something like that.
I had a question. Shouldn't for the matrix, or I forget what you call it, the vector, sorry, wouldn't it be negative 2i 1 instead of positive 2i? Because when you multiplied the bottom equation, you did it by times negative 2i to get the top equation.
Wait, so what are you asking me, Matteo?
So for the vector, right? I've thought it should be negative 2i and 1 instead of 2i and 1, because you multiply the bottom by negative 2i to get the top.
Okay. But if
Is
you
that
solve,
wrong?
well, I'm not exactly sure. I mean, if you solve the bottom equation, you get that x is equal to 2y times y.
I thought you said you get it be negative 2i times 1.
You thought that I said what now?
I thought you said that you multiply the bottom equation by negative 2i. in
So if
order
you
to get-
multiply the bottom equation by negative 2i, you get the top equation, okay?
Yeah.
I'm
And
with you.
so up to that point, then you go ahead and you get the identities. You get x equals 2y, y equals 2xi, and then the vector portion, that's where I got confused.
So hold on a second. So since these equations are multiples of each other, I can just forget about one of them because they're multiples of each other. And so I'm just going to concentrate on the bottom equation. And that bottom equation tells me x is equal to 2iy.
Ah, I see. So you can do that when they're, okay. So when they're equal, you can do that. Or like when they're, I forget,
Yeah.
somewhere around like coming out to be the same, you can do that.
When the equations are multiples of each other, you can just forget about one. Yeah.
Okay.
Okay, so here we are down here. All right, so now I want to get there. I want to split this. Hold on 1 second. But why wouldn't the top have, it does have that. So it does have that. So it does have minus 2ix is equal to 4y. That's right. And if you multiply, if you divide that equation, so let me just, let me do a little side work here in blue. So Abby says, wouldn't the top equation then say 4y is equal to minus 2ix? Yes, that is exactly right. Notice now what happens if I divide both sides by 2, you get 2y is equal to minus ix. And now if I multiply both sides by minus 1, you'll get, if I multiply both sides by minus 1, this is what you get. And then if I multiply both sides by I, this is what you'll get. And then if you multiply both sides by minus 1, this is what you'll get. So x is equal to 2iy. But to answer maybe what I think you're asking, Abby, if you start with something like 4y is equal to minus 2ix, you could solve this and get y is equal to minus 1/2 ix. And then so now you know that you'll have 1 here and minus 1/2 I. And to answer your next question, yeah, we just picked the simpler one. Absolutely. That's exactly right. Always pick the simpler one. But you could pick either one. So as long as you've done everything correctly, you could pick either one. You're just going to get an answer that looks different from what we're going to get here. But yeah, absolutely. Just pick the simpler one. That is the motto of my life. Figure out the easiest way to do it and do it that way. Those are good questions. I'm glad the two of you all asked those questions. Thank you. Okay. All right. Okay, so now here what we're going to have is e to the minus t. So in the parentheses, I'm going to separate everything into its real and imaginary parts. So I'm going to have cosine of 2t, 0, 1. That's definitely real. And then when I do I sine of 2t times that vector, I'm going to get minus sine of 2t times 2, 0. So this is like the real part. And then the imaginary part, how do I get an imaginary part? Well, if I do cosine of 2t times the I2, 0 vector, that's one way. So cosine 2t times 2, 0, or the I sine 2t times the real vector, plus sine of 2t times 0, 1. Okay, like this. And I can kind of combine this all. I'm going to combine it in the following way. E to the minus t. Okay, that first vector is going to be minus 2 sine of 2t. And the bottom entry is going to be cosine of 2t plus I. The top entry is 2 cosine 2t. And the bottom entry is going to be sine of t. Like that. sorry, this should be sine of 2t there. Okay. Oh, shoot, I'm running out of room. Oh, I'm on the second page already. So I'm going to have to erase this, and well, I'll just keep it there. So hold on. So let me just, I'm just going to copy what I wrote down, but up here. So this is e to the minus t times minus 2 sine 2t cosine 2t plus I 2 cosine 2t sine 2t. Okay, now it's easy to see what the real and imaginary parts are. Okay, and so the solution, the general solution, is going to be C1 times the real part. So that's e to the minus t minus 2 sine of 2t cosine 2t plus C2 e to the minus t 2 cosine 2t sine of 2t, like that. Okay, that is the general solution. Okay, that is a general solution. So when dealing with complex eigenvalues and complex eigenvectors, things are obviously tedious, but you got to know how to do it. Okay, are there any questions on this problem?
I guess just to clarify the method, we took the, like from when going all the way back to when we had the e to the like complex exponent and the complex vector, we just split e into its real and imaginary and then did the same to the vector and basically just foiled it.
Yeah, exactly. That's exactly what we did. We foiled it. So we had like a complex number times a complex number. We foiled it, separated that into its real and imaginary parts, and got down to this. Yeah, that's exactly how we did it.
Okay.
Yeah. Okay. Oops, hold on. So let's get on to this problem. Okay, so same setup as before. We're going to find the eigenvalues and eigenvectors. And remember, depending on the depending on properties of the eigenvalues is going to sort of dictate what happens next. But no matter what, we're always finding eigenvalues and eigenvectors. Okay, and so this is lambda plus 1, lambda minus 3 plus 4. Okay, I'm going to factor this, or not factor it, but the opposite of that, I guess, FOIL. So lambda minus 3 lambda plus lambda. So minus 2 lambda minus 3 plus 4. So this is lambda squared minus 2 lambda plus 1, right? And so I guess this is lambda minus 1 squared. Okay, so we just have one eigenvalue in this case. So I have one eigenvalue. Now we want to find the eigenvectors. So we want to solve the equation 3 minus 1 minus 4, 1 minus 1 minus 1 times xy is equal to 0, 0. Okay, so the top equation reads 2x minus 4y equals 0, and the bottom equation reads x minus 2y is equal to 0. Okay, notice the top equation is 2 times the bottom equation. So that gives us, that's a pretty good indication that we've done everything correctly. I mean, basically, even if we found the eigenvalues wrong and we came to this equation, we'd still get the eigenvectors right, okay? I mean, it's almost impossible to accidentally get two equations that are multiples of each other if you didn't get the right eigenvalues. Okay, so the bottom equation says, again, picking the easiest one to solve, the bottom equation directly tells us that x is equal to 2y. And so any non-zero vector where the top entry is 2 times the bottom entry is going to be an eigenvector. And that's the only eigenvector. We'll call this v. And lambda is equal to 1. Okay, so what do we do in the case where we just have one linearly independent eigenvector? What do we do?
Is this where we would find the generalized eigenvector?
Yeah, so we want to find the generalized eigenvector. The equation for that is going to be very similar to this equation that I just put in brackets, except instead of having a 0, 0 on the right-hand side, we're going to have the eigenvector on the right-hand side. And so the equation is going to be the 2 minus 4, 1 minus 2 times xy is equal to 2, 1. Okay, notice the top equation says 2x minus 4y is equal to 2. And the bottom equation says x minus 2y is equal to 1. Again, the top equation is 2 times the bottom equation. The bottom equation says x is equal to 1 plus 2y. Okay, and any vector, so we don't want a 0 vector, so any vector where the top entry is equal to 1 plus 2 times the bottom entry is going to work. So anything in general, anything of this form is going to work for any value of s, so long as the vector that we get is not the 0 vector. But that's never going to happen. There's no value of s that we can pick where both of these entries are going to be equal to 0. So we'll pick an easy one. S is equal to 0. So w is equal to 1, 0 is the generalized eigenvector. And then the general solution in this form, or sorry, the general solution in this case is x of t is equal to c1 e to the lambda tv plus, where v is the eigenvector, plus c2 e to the lambda t times tv plus w. Again, v is the eigenvector, w is the generalized eigenvector, and for this particular problem, x of t is equal to c1, so lambda is equal to 1, this is e to the t, times v to 1, plus c2 e to the t times t to 1, plus w, which is 1, 0. Okay, and this is kind of the form that we like to write it in.
I guess quick question on W. So we used 1 plus S but on top and S on the bottom. Would, if we like just like basically solve for Y, like so to say, like would 2S on top and S minus 1 on the bottom also yield?
Yeah, that also works, yeah.
Okay.
Yep. Okay. All right, seems like everyone's good there. So let's look at this problem. Okay, so we want to find the solution to this equation. So we have an initial condition. So this is going to involve two steps. One, finding the general solution, and then finding the solution to the initial value problem. Okay, eigenvalues, eigenvectors. Whoops. So Abby, to your question, I'm not going to do that. You'll watch some of the videos that I'll post tomorrow, because I don't know if the other classes are going to do that, so I'm not going to do it tonight. But look out for videos tomorrow. Okay, Abby? All right. You're welcome. Okay. So the determinant of 3 minus lambda minus 4, 1 minus 1 minus lambda. Is that the one that I just did? All right, that would be convenient if it was 3 minus 4, 1
Yeah.
minus.
I believe
Okay.
it is.
Yeah, so we know that the general solution is x of t is equal to c1 e to the t times 2, 1 plus c2 e to the t times 2, 1 plus 1, 0. Okay, we want to find the initial, we want to solve this initial value problem. Okay, so that means when t is equal to 0, x of t is equal to 1, 0. So we have 1, 0 on the left-hand side. Okay, now what happens when t is equal to 0? Well, we'll have c1 e to the power of 0 is 1. So that's 2, 1 plus c2. Okay, and now here, what happens when t is equal to 0? We just have 1, 0 left. All right, so this gives us two equations. The top equation is 2c1 plus c2, and the bottom equation says 0 is equal to c1 plus c2 times 0. Okay, so this bottom equation tells us that c1 is equal to 0, and then that implies that c2 is equal to 1. And so the solution to this initial value problem is x of t is equal to e to the t times t 2, 1 plus 1, 0.
So did you cross out like the determinant thing? Is that not relevant anymore?
Which determinant thing?
Just the one above like this workout, like crossed out.
Oh, sorry. That's just because so we first have to find the general solution to this differential equation, but it just happens to be that's the one that we just did.
Oh, okay, I see.
So let me write this. The general solution is from above. Okay. Okay, so I want to use the Euler method to estimate x of 0.2, where x is a solution to the initial value problem using a step size of 0.1. So basically, we know x of 0. We're going to use that we're going to use the Euler method to estimate x of 0.1 and use that to estimate x of 0.2. So the Euler method says x in is equal to, this is just equal to x of t in, this is equal to x of t0 plus n times h, and this is, approximately equal to x of n minus 1 plus x prime, plus f of tn minus 1 xn minus 1 times h, where this is f of tx. Okay, so we want x of 0.2. So the way we do this is we find x of 0.1 and we use that to find x of 0.2. So x of 0.1 is approximately equal to x0 plus f of tn minus 1, that's f of 0, times x of x0, which is 1, times 0.1. Okay, x0 is 1. Okay, if t is equal to 0 and x is equal to 1, this is just going to be 2 times 0.1 or 1.2. Okay, and this is what we call x1. And then x of 0.2 is going to be approximately equal to x2. x2 is equal to x1 plus f of t1 x1 times h, which is 0.1. So x1 is 1.2. Okay, t1 is 0.1 and x1 is 1.2. Okay, so f of 0.1, 1.2. So if t, so if x is 1.2, so let me put f in brackets here. X is 1.2. This is going to be 2.4. T is 0.2. So this is going to be, or sorry, t is 0.1. So this is going to be plus 0.3 times 0.1. This is 1.2 plus, okay, in the brackets here, this is 2.7 times 0.1, or this is 1.2 plus 0.27, and this is equal to 1.47. Okay, and so this is using Euler method to estimate that. Oh, sorry, I see the chat is lighting up. Sorry, hold on. Yeah, you're gonna need to actually add. So yeah, Abby, you'll need to actually add it. So it's going to be well on my exam. So again, for my exam, this will be a multiple choice question. Yeah. Okay. Okay, and these other ones are similar to the ones we looked at last week. Okay, so that's all.